In this video, we're going to talk about phase changes and the energy associated with those changes. And we're going to look at it through the heating curve. And we're going to talk about specific types of energy changes or the specific ranges of energy changes called heat of fusion and heat of vaporization. These are the terms, then, the energies that govern the phase change from solid to liquid and from liquid to gas. So on this slide, we have a picture of a typical heating curve. A heating curve is a crude phase diagram. It separates the different phases of a substance from solid to liquid and gas, measured against temperature, but a full phase diagram would actually include an axis for pressure as well. Here we take it for granted that the pressure is simply atmospheric pressure. So the assumption is that this is happening at atmospheric pressure, but the temperature is allowed to vary over some range. And we can see all three of the typical phases. Obviously, aqueous is not included. This is simply adding and subtracting energy from the substance in order to change its phase. This heating curve happens to be for water. So you can tell, I think you can spot the familiar signposts or the details about water. Well, let's take a closer look. Okay, so temperature, as you move through the different temperatures, you're adding thermal energy, or the x-axis here is thermal energy added. Oftentimes it's not actually specified how much specific energy is being added or subtracted. You simply have the x-axis or the horizontal axis as energy added, either in kilojoules or calories, doesn't really matter because there generally aren't any numbers. On the vertical axis, you have temperature, of course, given in degrees Celsius, sometimes in Kelvin. So as you move from left to right across the curve, you're moving from lower temperatures to higher temperatures generally, except for a couple of different plateaus or flat regions along the curve. And generally you are, as you increase in temperature, you are also moving through different temperatures of the same phase or moving across phases from one phase or physical state to another physical state. So the plateaus or the flat regions on this curve, those are points at which the temperature doesn't increase despite the fact that we are adding more energy. So the energy of point B is higher than the energy of point A. The substance has absorbed more energy at point B than at point A, or contains more energy, is holding more energy at point B than point A. Nevertheless, point A and B are at the same temperature, in this case, 0 degrees Celsius. This is water, and so 0 degrees Celsius represents the freezing point of water at normal atmospheric conditions. Likewise, between point C and D, point D has more energy than point C. Nevertheless, despite all the kilojoules of energy that were added in between point C and point D, the temperature did not manage to increase, but stayed exactly the same at 100 degrees Celsius. More or less. The lines are supposed to be aligned. Don't worry if they're not perfectly aligned, but they are supposed to be. So 100 degrees Celsius is the boiling point of water. So what does that mean? That these flat regions, these plateaus in the hill, in the upward sloping hill, of this heating curve, what do these plateaus represent? They represent the phase changes. So when you change from one phase to another, the energy that the substance either absorbs, if you're adding energy to it, or the energy that the substance releases into its environment, into its surroundings, if you're going from right to left, those are the energies of the phase change. That's how much energy is required to change phase, but those energy change, those physical state changes do not involve a change of temperature. All the energy that goes into the substance or gets removed from the substance is only involved in changing the physical state of the substance, changing the arrangement and changing the level of connectivity and attraction, or overcoming the attractive forces of the particles that make up the substance. Those attractive forces are the intermolecular forces we talked about, the electrostatic interactions, if we're talking about an ionic compound, the hydrogen bonding, or the dipole-dipole interaction, if we're talking about a polar covalent compound, or if we're talking about a non-polar covalent compound, a non-polar molecule, then it's the London dispersion forces. So those particular attractive forces are either being overcome when you go from left to right. When you melt, going in this direction from left to right, you are melting. And going from left to right over here, you are vaporizing. Going the opposite direction, let's see if I can use a different color here. Going the opposite direction, going from right to left, across this point, you are undergoing condensation, or you are condensing a gas into a liquid, and going from right to left over here, you are freezing a liquid into a solid. And thus you are not overcoming the intermolecular forces, but you are slowing down the particles so that the intermolecular forces can have take more of an effect and hold the particles even more closely together, more rigidly, and prevent them from being able to move very much. So these symbols here, this delta H FUS is the heat of fusion. That's called the heat of fusion, also referred to as the change in enthalpy of fusion. Remember, delta H also means change in enthalpy. Enthalpy is the heat exchanged at constant pressure. But for the most part, we're going to call this the heat of fusion, delta H FUS, and the heat of vaporization, delta H vape. These are two different energies, and other than sheer coincidence, these two energies are never even close to being equal. They do not equal. They are very different values. Delta H vape is often, delta H vape, the heat of vaporization is often going to be significantly larger than the heat of fusion. The heat of vaporization is often much bigger, because it takes a lot more energy to vaporize something than it does to simply liquefy something, if we're going from left to right. So the energy associated with vaporization, or in the reverse, the energy associated with condensation is much greater than the energy associated with freezing or melting. These energy terms allow us to calculate exactly how much energy is required, meaning absorbed or released, during phase changes. So there are only 2 points. There's either melting or freezing, that's 1 point, or vaporizing or condensating or condensing. Only 2 different points, only 2 different plateaus. And it's important to understand that the delta T, the change in temperature at those points, is 0. If the change in temperature is 0, that means we cannot use the formula m times c times delta t, because what is delta t at the phase changes? So if we're trying to calculate the energy associated with phase changes, and we try to apply Q equals mc delta t, we're always going to get a value of exactly 0, and that's wrong. Obviously, it's wrong. In fact, phase changes require much more energy than simply raising or lowering the temperature of a liquid, a solid, or a gas. We're going to see that to change the phase, to change the physical state from a solid to a liquid or a liquid to a gas of a given quantity of substance actually requires much more energy than to raise or lower that temperature of that substance in a single physical state from its freezing point all the way to its boiling point, because it's a very energy intensive process. But why is it so energy intensive? It's because you have to overcome intermolecular forces when you change phase. Let's just do a brief review of the different phases before we continue. In the solid state, atoms or molecules are rigidly held in fixed positions and forming a solid with definite volume and shape. The particles are unable to move out of their positions, but they can vibrate, but they can't move, they can't change position. They must remain in contact with each other, not only in contact, but in a solid. Remember, they occupy those rigid positions in a lattice. Remember, we have every type of compound other than amorphous involved the organization of the particles, whether they're atoms or molecules or ions. Every one of them involve the organization of the particles that make up a solid into some sort of repeating pattern called a crystalline lattice or crystalline structure, where all the different particles occupy the same position relative to one another. Liquid phases have no crystalline structure. They are always in contact. Now, in a liquid, the particles are always touching each other. It's just that they're not always touching the same particle. One particle will be in contact with another, and then another, and then another, but they will still be touching the whole time. They'll still be different particles in contact with each other, but they will move around amongst each other like a crowd of people, just moving about, but still always crowded together. There's no fixed position. They are not held in a fixed position, but they are always in close contact. The particles move or slide around each other. There's definite volume in a liquid. That's why we can measure the volume of water, for example, or any kind of solution. But there's no definite shape other than the shape of the container you pour the water into. If you pour the water into, for example, a long, narrow tube, it takes the shape of a long, narrow cylindrical tube. If you pour it into a wide square or cube-shaped cup, it becomes a cube. In other words, it'll take on any shape, but the volume will always remain the same. Solids, on the other hand, maintain their own shape. You can't squeeze a solid into a different shape without cutting or bending it. And in the gas phase, we know that gas phase have no definite volume, no definite shape. Gases will take on the same shape of whatever container they're stuck in, and you can almost seemingly infinitely expand a gas, or you can compress it down to almost nothing in terms of volume. So you can expand its volume, make it huge, the size of a planet, like, for example, the gas giant Jupiter. That's a gas planet. There is no solid rock Earth. It's a gaseous planet. The gases, yet it's a planet that could fit thousands of Earths inside. So you can expand a gas indefinitely, and you can also compress a gas to almost no volume at all. But of course, nothing occupies zero volume. But you can crush a gas to a very tiny, tiny space. Eventually, though, you risk liquefying the gas. So you might end up with no gas at all, but with a liquid instead. Okay, so those are the different characteristics of the different physical states. So thermal energy and phase changes are represented with this heating curve. And here is just a sort of representation, a visual representation of the different physical states. Here, in the first part of this curve, we have the solid. Before you reach the freezing point, you have a solid. Solid, the particles are stacked on top of each other in that close pack sort of crystalline arrangement. In the liquid phase, there's no more organization. So we have the liquid phase from here to here. And that's represented, notice the particles are still touching, but they're rolling around. They're moving around each other. They're just kind of rolling around. In the solid state, they are rigidly held in place. However, the particles are able to vibrate. They do vibrate back and forth. If you get them vibrating enough, they'll eventually break free, but you have to give them a lot of energy. And as you supply energy, everything I'm saying, by the way, I'm always going to talk first about going from left to right, just because it's easier to understand a substance absorbing energy and becoming more energized. But everything I'm saying applies equally well in the opposite direction. As I remove energy from a substance, it goes from the gas phase to the liquid phase to the solid phase, and those intermolecular forces take greater and greater hold, take greater and greater effect. And the particles become less and less free, more locked down by their attractive forces. And then finally, after the boiling point, after this phase change here, the heat of fusion, heat of vaporization, we have the gaseous state or the vapor state. And that goes on up to a point called the critical point, which we're not really going to talk about in this class, but there is such a thing as the critical point, a temperature beyond which you can no longer liquefy a substance, but its gas and liquid states are interchangeable and inseparable. They cannot, there is no change. So in the gas phase, you have particles that are no longer touching. Instead, the particles are blasting off in their own separate directions, other than colliding by chance once in a while if they happen to be locked in the same container. The particles are free to roam around and are no longer in contact. At this point in the gas state, the intermolecular forces, the IMFs, can be said to be completely overcome. All those attractive forces have been overcome by the amount of energy that has been added or absorbed by the substance. It takes energy to get these substances to move, to overcome their attraction to each other and to start moving away from each other. In the liquid phase, the IMFs the intermolecular forces are only partially overcome. Partially, meaning that while you've weakened or you've given the particles, the liquid particles, enough energy to sort of maybe loosely relate to each other, they've been loosened up, but they haven't been completely able to break free from one another. In the solid state, on the other hand, the intermolecular forces are rigidly holding those particles together. They are glued together. They are Velcroed together, as the analogy goes in the previous video. They are Velcroed together and they're not able to break free. They're not even able to move around. So as you add more and more energy, the particles loosen up until they're completely free gas particles. Until then, they are trapped. Think of it this way, the so-called condensed phases of matter, which are the solid and the liquid state, the so-called condensed phases of matter are simply frustrated gas particles. They're just gas particles that have been trapped by their own intermolecular forces due to the lack of thermal or kinetic energy because of the lack of thermal energy. But as they gain kinetic energy, what do gas particles do when they have kinetic energy or when the temperature rises? They gain kinetic energy, energy of motion, and they're free to move. Well, liquids and solids are simply the other direction extension of that. As you take away kinetic energy, the particles slow down and eventually just coalesce into liquids and then finally solids. You add thermal energy and you break them free from their bonds. They're intermolecular bonds. We know that intermolecular bonds are not true bonds. Just remember that. These are not covalent bonds or even ionic bonds. These are simply intermolecular forces of attraction. They are not true bonds, and they are weaker than covalent bonds or ionic bonds or metallic bonds. And that's why they can be overcome with just a little bit of heat. When you heat up, for example, when you heat water, when you give it enough heat to go from liquid to the vapor phase, you've separated the water molecules, you've overcome the intermolecular forces, but by no means have you broken even a single hydrogen-oxygen covalent bond. There's no way. That's a lot more energy than what you've added just to change phase of water. And this is true for any other substance. So the idea here is that the different phases are governed, the phase changes are governed by heat of fusion, delta H FUS, the heat of fusion, and the heat of vaporization. These are the energies associated with changing phases, either adding energy to go from solid to liquid and liquid to gas, or taking away energy going from gas to liquid and liquid to solid. In between, the energies that govern the in-between part, like for example, from 0 degrees Celsius in water to 100 degrees Celsius, or in this case, negative 126 degrees Celsius for whatever this substance is, to 96 degrees Celsius from its freezing point to its boiling point, that is governed by the specific heat. If you want to calculate the energy of changing the temperature, that's the same old Q equals MC delta T. But you cannot use that formula to calculate energy at the phase changes because there is no delta T. But in between phases, you can see that as you add more energy, the temperature of within a physical state, within the same physical state, increases and increases until you get to the boiling point. Then you have to add you calculate the energy using the heat of vaporization to calculate the phase change. Once you have a change in physical state, now, once you're into, say, for example, the gas phase, now adding heat raises the temperature of the vapor or the gas. And as you add energy, the temperature of that gas goes up. So you can have a very hot vapor or a relatively cool vapor. But one thing remains true, that all vapors contain more energy than their liquid counterparts, even at the same temperature. Steam, for example, at 100 degrees Celsius contains a lot more energy than liquid water at 100 degrees Celsius. You may say, well, at 100 degrees Celsius, I thought water boils. Well, yes and no. Water will start to boil at 100 degrees Celsius, but you can still have 100 degrees Celsius water before it actually boils and becomes a vapor. Also keep in mind that the boiling point is technically only the point at which the vapor pressure of water happens to equal the local atmospheric pressure. Well, if you're below sea level, your atmospheric pressure may very well be higher than 760 millimeters of mercury, or higher than 1 atmosphere, which means your water might not even boil at 100 degrees Celsius. So you might have just hot liquid water. Hot liquid water contains a lot less energy than vapor of the same temperature. Why is that? Because vapor is on this side of the curve, the delta H vaporization, the heat of vaporization. Vapor or gas is on this side, liquid is on this side. If I could write a little bit neater, that would be great. Here, liquid. There's only so much thickness. So there's this much extra energy. Now, it looks like there's not much, but the truth is this is a very large amount of energy. Large amount of energy, usually more energy than it takes to raise the temperature of a given quantity of water from 0 to 100. It contains more energy than all that. It doesn't look that way only because this curve, this heating curve, is not to scale. If it were, this plateau region would probably be a lot longer, but that would make for an ugly and hard to read curve. So the gas phase is going to have a lot more energy despite the fact that it's at the same temperature of the liquid phase at 100 degrees Celsius. That's because all that extra energy went into separating the particles, the water particles, or whatever the substance's particles are. A lot of energy went into separating those particles. So if you have the choice between being exposed to water at 100 degrees Celsius versus vapor or steam at 100 degrees Celsius, well, you may want to choose the liquid water. On the other hand, the vapor is a lot less dense, so you might not get as much coverage. So it's kind of hard to tell, but gram for gram, or gram for gram, or volume unit for volume unit, steam does have more energy, and it can burn a lot worse than what liquid water can at the same temperature. But yeah, you do have the lower density going for it. Same thing I say applies to I said about liquid versus gas applies to the solid state, ice versus liquid. The liquid at 0 degrees, well, this is not, I keep talking about this as if this is water, but this is some other substance. At this substance's freezing point, the liquid has a lot more energy than the solid, even at the same temperature, because the liquid contains a lot more added energy. How much more energy? The heat of fusion amount of energy multiplied by the number of moles. Heats of fusion are typically reported in kilojoules per mole of the substance. They're not usually reported in grams, although they could be. And notice there is no temperature unit. Unlike specific heat, there's no temperature unit because it always happens at the same temperature. At a fixed, I'll say not at the same temperature, but at a fixed temperature. Usually that fixed temperature for heat of fusion is at the freezing temperature, and for the heat of vaporization, that temperature is at the boiling temperature. but these always occur. These energies, heats of fusion, heats of vaporization, are generally reported kilojoules per mole rather than per gram, per mole of substance, and no temperature unit is included in that compound unit because it's already assumed there is no delta T change, so it's not per any amount of temperature. It's not per degree Celsius or per Kelvin. Okay, let's go through a concept check here. Let's walk through questions here. So refer to the following heating curves. This is yet another substance's heating curve. Notice the temperatures don't correspond to liquid, don't correspond to water at all. Refer to the specific heating curve and the specific values of A, B, C, and D. I put them over here. This is for my purposes only so I can have some flexibility. I can ask this question in many different ways, so I can give you different energy units, and that changes some of the answers here. It doesn't change the answers to question number 1 or 2, though. These will always, and in fact, even question number 3. These will always be the same answer regardless of what numbers I put in place for A, B, C, and D, because those depend only on the shape of the curve and the actual temperatures where we have our plateaus. So question number 1, what physical state is the substance in at a temperature of negative 175 degrees Celsius? So here we have our temperature axis, our vertical axis, given in degrees Celsius, negative 105 degrees Celsius. Now, this only goes down to negative 110. So negative 175 presumably would be way down. Sorry, the computer's moving. Would be way down here somewhere, right? Negative 175 degrees. But we don't know exactly where it's going to intersect any kind of x-axis. The good news is it doesn't actually matter, right? There are only 3 physical states, solid, liquid, or gas. We're not talking about dissolving anything. Those are different energy components, actually, and that's not something we're going to cover in this class, the energy of solvation. So negative 175, what do you think, what physical state do you think that will be in? If negative 110 is to the left of this plateau, and negative 175 should also be to the far left of this that plateau. So what physical state is it? Pause the video and think about it if you want. Okay, I assume you're back. So you want to know the answer. It's going to be in the solid state. Solid. Anything to the left of this point right here, or of this plateau, anything to the left is solid. It doesn't matter whether it's on the graph or not. Turning something, making something even colder isn't suddenly going to reverse the physical states and suddenly turn it liquid again. That doesn't work that way. Nature doesn't work that way. If it's solid at negative 110, it's going to be solid at negative 175. It's going to be solid all the way down to absolute 0. In fact, it's only going to get more solid, right? If such a thing even exists. And it does, properties do change as you get colder and colder and colder, but it will always remain solid. It will just be different types of solids. For example, you may not have heard this, but ice, water ice, actually there are about 25 different kinds of ice depending on temperature and pressure. The ice that we know, right around negative 0 degrees Celsius to negative 20 degrees Celsius, the kind of ice we know is less dense than liquid water and floats in water. However, if you keep cooling ice down some more, down to negative 50 degrees, negative 100 degrees Celsius, getting closer and closer to absolute 0, you actually reach a point, they're all solid, but you actually reach a type of ice right around the negative, I think it's the negative 50 degrees Celsius mark, where ice actually takes on a structure that is more dense than liquid water. So if you cool ice down enough, it will actually change forms and become more dense than liquid water, and you'll actually dropping that ice cube into water, the ice cube will actually sink in the water. So there are different types of solid. The solids rearrange as you go further down the temperature scale. but they are all still solids. So negative 175 doesn't matter where it is. The point is this compound is already solid below negative 29 degrees Celsius. Anything past that point, lower than that point, is just going to be more solid. Okay, so let's go to the other end. What physical state is the substance in at a temperature of 93 degrees? 93 degrees. Well, where is 93 degrees located on this curve? Well, I have this as a guideline here. We have 82 degrees. So this line right here represents 82 degrees Celsius. So 93 is going to be somewhere over here on the curve, just guessing. So what physical state is this to the right of the heat of vaporization plateau? If you're at a point to the right of this region here, what physical state are you in? Obviously, you're in the gas phase because you've heated it up past its boiling point. You are now in the gas phase. So gas phase, solid phase, anything less than negative 129 is solid. Anything higher than 82 is gas. And 93, last I checked, is greater than 82 degrees. So that's how you can tell. And of course, anything in this region right here, any point in this region is going to be liquid. Anything between negative 29 degrees Celsius and 82 degrees Celsius, greater than negative 29 or less than 82, this substance, whatever substance X is, we don't know, is going to be in its liquid phase. So liquid. So that's how you look at this curve in that way, but there is more to this curve than just that, as you know. So let's ask some more questions now. And I'm just going to clear up some of this. I'm just going to declutter this right now. If you want these, you can always just rewind the video and go back and look. Okay, but let's declutter because I'm going to need some room. Not a lot. These aren't major calculations, but I'm going to need a little room. What is the boiling point of this substance? Well, that I think you know already. That's exactly where the temperature at which you've got this plateau. The second plateau, the rightmost plateau, there are only ever two flat regions, right? There's the one for freezing and melting, and there's the one for boiling or vaporizing and condensing. So this one is the boiling. This is where you'd put your boiling point. 82 degrees Celsius. So you just read these. These first three are read right off of the curve, or at least implied by reading the curve directly. No calculation, no math needed. Just look at the numbers and think about what number you're at or what number you're to the right of or to the left of. You're basically moving left and right along this curve when you're moving through the phases or physical states that a substance can be in. So 82 degrees Celsius would be the boiling point. That's the point at which the vaporization of the substance is initiated. You can assume that this substance is being measured, or all these physical state changes taking place at these particular temperatures is at 1 atmosphere. Just assume you're at standard atmospheric conditions. If you were not, or if you wanted to vary the atmospheric or the pressure, you would have a third axis coming in and out of the screen. And that would be a true phase diagram. Phase diagrams are more complex looking. They actually involve different pressures as well as different temperatures and different types of phases, including the different kinds of solid phases. Even liquid phases have different phases. Water can actually exist in 2 different liquid phases, and that's only been recently discovered. So even liquids have phases. It's very odd. I mean, we think of liquids as being this amorphous jumble of molecules or atoms, but actually they can also take on some level of structure even in the liquid phase, because those intermolecular forces are still guiding the interactions of the particles. All right, so that's questions 1 through 3 read straight from the graph, somehow just reading the graph. Now, 4, 5, and 6 are going to involve just a little bit of calculation, but these are just concept check type questions, okay? These are not even the real calculations that we're going to get into as far as calculating energies of phase changes of specific quantities of substance. All right. So just doing a little house cleaning here. What is the heat of fusion? The heat of fusion, remember the heat of fusion is delta FUS. This is the term that governs the solid to liquid interconversion, the solid to liquid physical state interconversion. What is the heat of fusion of this substance in kilojoules per mole? Well, luckily, I've labeled this in kilojoules per mole for your convenience, but that's not the answer, right? We have to figure out the answer. We have to figure out first, where's this heat of fusion located? Well, I hope by now you know at least to look for the flat portion of the curve. So I hope you don't look for it in one of these diagonal portions. It's definitely not here, definitely not here, and definitely not here. Because those are not physical state changes. Those are not phase change regions of this curve. So I hope by now you know at least to look for the flat portions of the curve, which would be only two options, and you only ever have two options. It's either going to be this one, or it's going to be this one. Which one is it? Pause the video now if you want to think about it, or you want to go back and look at the notes. Okay, so I assume you looked at your notes, or you already know the answer. And so the heat of fusion again refers to the liquid to solid, or solid to liquid energetics, or the energies of physical state conversions between solid and liquid, and that's going to be the colder temperatures and the leftmost temperatures right here. So this is our delta H fusion. This region right here from A to B. From A to B is our heat of fusion. So what is it? So going from A to B, well, if we're looking at the numbers over here, how much energy was input into this substance or removed from this substance across the point A to B? Well, since it's saying heat of fusion, it doesn't really matter. I'm just going to take the absolute value. Don't worry. Right now, for this question, the heat of fusion will just take the absolute value. We'll take a positive number because generally speaking, you don't try to report these numbers. These numbers aren't given in negatives, right? It's just an energy, the amount of energy per mole. Don't worry about how many moles right now because it doesn't matter. The units here are in kilojoules per mole. So what do? We just take the difference between A and B. The change in A and B equals, I'll take the bigger number minus the smaller number for no particular reason other than that I don't feel like dealing with negative numbers right now. They're both in the same units, they're in kilojoules. Technically they're in kilojoules per mole, right? I didn't actually write that, I probably should have. It's implied, right? You guys know it's implied. All right. So we have 16 minus 8 is 8. 3 minus 1 is 2. 2.81. If I've done my math correctly, that should be 2.81 kilojoules per mole. And so that is the answer to this question. 2.81 kilojoules per mole. That is our heat of fusion. That means to go from liquid to solid, we have to remove or we have to subtract. We have a negative 2.81 kilojoules for every 1 mole of substance. If we're going from solid to liquid, then we add 2.81 kilojoules or 2,810 joules of energy to every mole of this substance, whatever this substance happens to be. So we're just taking the difference, the amount of energy, the energy change across from A to B, the delta E, which we have the values right here. I didn't put them on the graph because I can always change the numbers this way. That, and it's very hard to write on this graph. Okay, so hopefully that makes some kind of sense. Question number 5, how many kilojoules absorbed or released when 0.288, now we're getting to specific quantities, when 0.288 moles of this substance condenses. So condenses, first of all, as far as the sign goes, you don't even need to do the calculation to figure this out. Condenses, what does condensation mean? Condensation or condensing is when you go from gas to liquid, right? That's the definition of condensation or condensing. Gas to liquid specifically. So is the substance gaining energy or losing energy when it goes from a gas to a liquid? Well, which state is the higher energy state? Gas is the higher energy state. Liquid is the lower energy state. You're actually moving from right to left on the curve. That's, I mean, I know I wrote it this way, but on the curve, you're moving from right to left, going from gas to liquid. So this is a situation where you are, it's a big negative. The substance is losing thermal energy. It's going from gas to liquid, it's losing thermal energy. So that's a big negative on there. So the reason I say that is because that way you don't have to think about what the math tells you to do. Just take the difference between points, between the points on the curve that you need to take, and then just put on the right sign. If it's a positive, make sure you turn it negative. If it's negative, if your calculation ends up giving you a negative, great, because that's the number, that's the sign that you need. That's the, the negative or positive sign. I don't mean like a cosmic sign. Okay, so where are we now? Where are we on the curve? When we're talking about condensation, where on the curve are we? Again, because this involves a physical state change or a phase change, I hope you know better than to look at the diagonal portions of the curve. The diagonal portions are not it, so ignore this. For phase changes, it's not going to be this point, it's not going to be this part of the curve, it's not going to be this part of the curve. Condensation is between gas and liquid, so we know that that's going to involve the delta H, or the heat of vaporization. It's going to be between C and D. That's going to be our area of focus. The energy between C and D. Technically, because we're going from D to C, we're moving from right to left, we're going to take, since C is our final, we're going to take C minus D. That'll actually give us the negative number. But if you don't do it that way, if you simply take the difference, it's okay. Just understand that you need a negative sign to indicate that energy is being released from the substance into the surroundings. So if I take C minus D, I'm taking a smaller number, 5.33 kilojoules, minus a bigger number, 11.74 kilojoules. Per mole, right? There's an implied per mole there. I should have probably written that there. I'm sorry about that. So 5.33 minus 11.74, we can figure out our heat of vaporization, our heat of vaporization. Uh, 11.74 minus 5.33 gives me 6.41 kilojoules per mole. Okay, but that's not our answer, because that's 6.41 kilojoules per how many moles? Well, obviously it's per mole, which means it's per 1 mole. Do we have 1 mole? No. The question tells us that we have a little bit over 1/4 of a mole, or 0.288 moles. So we don't have 1 mole. So we're going to expect that this is going to take less energy than 6.41 kilojoules, because we don't have 1 mole, we have less than a mole, it should take less than 6.4 kilojoules. So what do? Well, we set up our typical dimensional analysis. In essence, the heat of vaporization and heat of fusion are nothing more, again, than just fancy conversion factors. That's all we've been doing. Most of the math we've been doing has been nothing but conversion factors. We're simply moving from moles of substance to energy. So if I take my 0.288 moles of this substance and I multiply it by the conversion factor, that tells me every 1 mole of the substance requires 6.41 kilojoules of energy to change phase from liquid to gas, or gas to liquid. Then we get 0.288 times 6.41. That should give us about 1.8 or something. I don't know. Let's see, 0.288 multiplied by 6.41. Really? That's way off. 0.288. Where did I go wrong? 1/4 of 6 is 1.5. Huh. Okay, well, whatever. Anyway, my calculator is probably telling me the truth. I'll have to rethink my math here. So 0.0449 kilojoules. So the moles cancel out. Just like in any dimensional analysis problem, the moles will cancel out, and I wind up with kilojoules of energy. So it's going to give us, I should have asked this in joules. How about in joules? How many kilojoules? Maybe it would have been better to ask this in joules, because then at least we could get 44.9 joules instead of 0.0049. Tell you what, okay, let's do this in joules. It's easier to report. 1, 2, 3. 44.9, I'm just moving the decimal over, 44.9 joules of energy, and that's our answer. We took the 0.288, we got kilojoules, and then all I did was divide by 1,000 kilojoules per joule to convert this to joules. Sorry, that's going to look a lot more confusing later on. I'll just write them, I'll write them both down. 0.0449 kilojoules or 44.9 joules. Either one of these is the answer. Since I asked originally for kilojoules, but the number is so small, it makes more sense to get joules than kilojoules. So how do we, again, the important part is that you understand where this 6.41 came from. It came from the difference between point C and point D. That's the amount of energy spanning this flat region of the curve. This is the energy associated with the heat of vaporization. It takes this much energy per mole of substance to either liquefy the substance from a gas or to vaporize the substance from a liquid at a temperature of 82 degrees Celsius, which we're assuming that's where the temperature we were at. So if all we're trying to do is convert this from a gas at 82 degrees Celsius to a liquid at 82 degrees Celsius, then 44.9 joules is how much energy that process takes. And remember, this is a negative sign, right? This is release because you're going from gas to liquid. So this is the release of that much energy into the surroundings. The substance is losing that much energy. It's going from right to left. So the change in energy is C minus D, because we're going from right to left when we're going from gas to liquid. Okay. Question number 6, what is the specific heat? Now this actually is a little bit of a toughie. I've never asked this question before, so, but since, you're watching this video, we can actually try and calculate this. This one's an interesting question. It's going to take a fair amount of calculating, not a lot. It's still just subtraction, adding, multiplying, dividing, whatever. But so let me I'm talking while I'm cleaning up here. To figure out the specific heat of the liquid, different physical states have different specific heats. So for example, we learned that water has a heat capacity of 4.184 joules per gram Celsius, right? But ice has a different heat capacity. Steam has a different heat capacity from the liquid. So if we're looking at the liquid here, we're looking from here to here. We're looking at the change in energy. We're looking at the change in energy and the change in temperature for 1 mole. Well, it's assumed here that this is 1 mole of substance, so we don't have to worry about the moles. So what we need are the kilojoules. We need the kilojoules related to the change in degrees Celsius. In other words, we need the delta E over the delta T multiplied by mole. And again, remember, this is implied that it's already per mole, so we don't really have to do any calculations involving moles here. So what is our specific heat? All we do is we go from point B to point C. We calculate, let's calculate this one at a time. Let's calculate delta E first. Delta E, the change in energy in kilojoules. Delta E is going to be our temperature C minus the temperature B, the energy at that point. So that's going to be, let me just give myself some more energy. C minus B, we have C, we have B, 5.33 kilojoules minus 4.7 kilojoules. And that's going to equal 0.63 kilojoules. By the way, notice this is a relatively small number. All the numbers we've gotten so far have been greater than 1 for these phase changes, but the entire span of the liquid phase only gives rise to a fraction of a kilojoule. And that's usually how it is. It takes a lot, like I've been saying, it takes a lot less energy to warm something up that's in one phase than it does to change from one phase to a different phase. Phase changes are very energy intensive. Whether you're gaining energy or losing energy, they involve a huge amount of energy change. So far we've got the top half of our specific heat. It's going to be 0.63 kilojoules per delta T. Okay, so delta T is going to equal what? Well, going from point B to point C, we change temperature. We take the temperature at point C, that's going to be temperature at point C minus temperature at point B. That's going to equal 82 degrees Celsius minus negative 29. Now be careful, when you're subtracting a negative, you are adding, so be careful with that. So that's going to be 82 plus 29 degrees Celsius. Minus a minus is plus, right? So we get 82 plus 29, that's going to be 100, is that 121 or 111? You know what, I'm going to make sure I do this right for you guys. 111. So that's 111 degrees Celsius. So those are 111 Celsius degrees. So 111. So in other words, we spread 63 kilojoules over a span of 111 degrees. So when we take this and we divide 0.63 divided by 111, and again, I probably should have used joules instead of kilojoules. 0.63 divided by 111 gives me, wow, 0.05, no, wait, hold on, 0.00568 kilojoules per mole degrees Celsius. Notice this mirrors the specific heat, except instead of using grams, I'm using moles. We could have also reported the specific heat of water back when we learned it, 4.184 joules per gram Celsius. We could have reported that in moles just as easily. 4.184, I'm using this because I think you're familiar with it, joules per gram Celsius, right? You're familiar with this as the specific heat of water. We could have easily converted grams to moles by dividing by 18 grams per mole. And we could have reported this number by dividing by 18. We could have done joules per mole Celsius, and it would have been the same thing. There's nothing fundamentally different about this. If we knew the molar mass, we could actually convert these moles to grams, and we could report this as kilojoules per grams. But because this is an unknown substance and I didn't give you a molar mass, we don't actually have that. This looks really strange. So you know what I'm going to do? For question number 6, this is the technical answer because I asked for kilojoules. I guess technically this is the right answer, but I'm just going to convert this to joules. 1, 2, 3. So I'm just going to write this as an alternative because to my eyes, this looks neater. 5.68 joules per mole Celsius. If we knew the molar mass, we could actually convert this to joules per gram Celsius, just like a normal specific heat. So this is the specific heat of the liquid phase of this unknown substance. This indicates what? Does this indicate, is this substance a better or worse thermal conductor? Sorry, you know what, let me answer. I should have asked this as one more question. Is this a better thermal insulator? Let me ask it the other way. Thermal insulator. As a thermal insulator, is it a better thermal insulator than water or a worse thermal insulator than water? Think about that. Is this a better thermal insulator or a worse thermal insulator than water? Given the value, oh, we don't know, do we? Or do we not know? I just realized we don't know. We can't possibly answer this question, can we? Yes, we can. Of course we can. How do we make this comparison? We may not know the grams of this substance, but we do know the moles of water, right? So let's try that. Let's make the comparison here. I should have made this question number 7. How do we compare them? Well, we can't simply straight up compare 4.184 joules per gram because grams are not the same thing as moles. And we can't convert this to grams because we have no idea what the molar mass is. But what we can do is what I just suggested, 4.184 joules for every 1 gram degree Celsius is the specific heat of liquid water. What we can do is we know that every 18 grams of water is 1 mole of water. So if we multiply that out, the grams are going to cancel and we're going to end up with moles on the bottom. So 4.184, I think I misspoke and said you had to divide earlier. Sorry about that. So 4.184 times 18 gets us 75, oh boy, 75.3 joules per mole degree Celsius for water. That's the specific heat of liquid water in joules per mole Celsius. So now we can answer the question, is this substance, whatever it is, does it have a higher or lower, is it a better or worse thermal insulator? Well, I guess on a per gram basis, I suppose we could say or on a per mole basis. We can only compare them per mole. We have no idea what the mass is, but on a per mole basis, is it better or worse? Well, it's far worse. In fact, compared to water, this is downright a good thermal conductor because we have such a low value of energy per mole compared to that of water. Now, it could turn out that its molar mass is very, very low, but it's hard to imagine a molar mass that is less than 18 grams per mole and still have some kind of significant kind of material. So chances are this is a much worse thermal insulator and a much better thermal conductor than water. It's a terrible thermal insulator is the conclusion here. Because it has an extremely low specific heat, which means its temperature can change very quickly and very easily with just a small amount of energy added or subtracted from it. So this is a worse, much worse thermal insulator than water on a per mole basis, and most likely on any basis. Okay, so that's our little concept check. That's just to see that if you can answer these, then you know your way around a heating curve and you've understood the ideas or the underlying concepts of heat of fusion, heat of vaporization, and more or less how to use them. But we're going to look at some more specifics here. We're actually going to run through a different kind of question, very similar, but we're going to actually look at not just the phase change energy, but the energy to go from a temperature within one phase to another temperature in a different phase. So let's take a look at that. So here's a fairly typical kind of question that you might get. Calculate the kilojoules, the energy associated with converting 80 grams of ice, this is water ice, by the way, this is going to be for water, at an initial temperature of -15 degrees Celsius. Now notice, we are not at the freezing temperature. We are at a temperature below freezing. -15 degrees Celsius ice to water at a temperature of 75 degrees. So we're going from very, very cold ice to warm water, very, very warm water. So we're not just moving from one state or one physical state to another. We're not just phase changing, we're also heating or warming up the two different phases. This is going to involve several different calculations, and then we're going to sum up the energies for all three parts of this. So this is the information that we're given. And the only thing I want you to memorize from this list is the same thing I've always been saying, the 4.184 joules per Kelvin grams. By the way, Kelvin, whether I put kelvins or Celsius, it's the same thing. Remember, 1 Kelvin unit equals 1 degree Celsius. And since we're taking it per Kelvin, a per Kelvin and a per Celsius are exactly the same thing. Per Kelvin means exactly the same thing as per degree Celsius. Now, if you tried to multiply or divide or add those temperatures, then you would not get the same thing. Don't do that. You can't treat kelvins and Celsius interchangeably, except in this one instance where I say per Kelvin, because it's per 1 unit of Kelvin. And a unit of Kelvin, if you recall, is the same as a unit of Celsius, because the Kelvin scale was developed from using the Celsius scale to measure the coldest temperature that a gas could achieve, where it becomes zero volume from the Charles's law sort of experimentation, as you remember from module 11, from the gases module. Okay, so this is the only number I want you to remember. Basically, it's the conversion between joules and calories. Other than that, you don't have to memorize any of these other values. So these are the pieces of information you will have to do this problem. You have all of these available to you. Now, there's more information here than you actually need. I've given you all the 5 different pieces of thermodynamic data. Every part of the heating curve is covered by each one of these thermodynamic expressions, or these thermodynamic constants for water. Okay, so I'm just going to outline the solution to the problem, but then we're going to walk through the problem itself. So this problem requires 3 different steps. Step 1 is going to take us from -15 degrees to 0 degrees Celsius. That's the energy right here. That's the energy of step 1. The energy of step 2 is going to involve the energy transformation from solid ice to liquid water. That's our energy step 2. And then finally, energy step 3 is going to involve, step 3 will calculate the energy to warm up the water from 0 degrees Celsius. Remember, this is still 0 degrees Celsius on this side, all the way over to 75 degrees Celsius. So we're going to involve 3 different terms, and we're going to calculate 3 different energies, and then we're going to sum up those 3 different energies. So first we're going to calculate the warming up of ice. I know that sounds strange, but ice will be warmed up without actually melting. Remember, ice can get super cold. You can have different temperatures of ice, just like you can have different temperatures of water. So we're going to use 3 different terms. We're going to use the specific heat of ice. We're going to use this one right here for step 1. And we're going to calculate Q equals M times C times delta T for ice. The temperature change for ice from 0 to 15, or actually I should say from -15 to 0. That's going to be our delta T. We're going to calculate Q. We have 80 grams of ice. Remember, the grams don't change just because you're changing physical state. It's all 80 grams. That's step 1. Step 2, we're going to melt the ice at the same temperature. That's going to involve the heat of fusion. That's step 2. Melting the ice. No delta T. So that's simply a conversion of moles to kilojoules. Moles to kilojoules using the heat of fusion information. And then finally, we're going to warm up the water. That's going to, once we have water at 0 degrees Celsius, we're going to warm it up from 0 degrees Celsius to 75 degrees Celsius. That's going to involve the specific heat of water. That's our step 3. That's going to be Q equals M, which is still 80 grams, times C of water, specific heat of water, times our delta T for the water, which is going to be 0 to 75 degrees Celsius. This is going to be negative 15 degrees Celsius to 0 degrees Celsius. So that's how this is going to work. And then step 4 is just to add up all of these, add up steps 1 through 3. That's going to be step 4, and that will give us our final answer. It's a long process and it's a long calculation, but it's mostly just number crunching. So step 1, and I've outlined them right here, step 1, step 2, step 3. Then step 4 is add up all 3 energies. By the way, be careful about units. Step 2, melting, is going to give you units of kilojoules. So be careful. You will get your units in kilojoules for step 2, but the other ones will be in joules for steps 1 and 3. Remember, melting or warming up a substance without changing its physical state is actually a relatively low energy process. Phase changes are high processes because they involve the overcoming of intermolecular forces. Warming something up doesn't overcome any intermolecular forces. You're just loosening up what's already loosened, or what's already there. Okay, so let's take this one step at a time. So step number 1. Step number 1, warming up the ice. Let's warm up our ice. How much energy does it take to warm up the ice? Q equals M times C, specific heat of ice, times the delta T of the ice, the change in temperature of the ice. So we have the mass of the ice, that's 80 grams, that comes right from the problem. 80 grams, multiplied by the specific heat of ice. That is not the same as water. It's 2.02 joules per Kelvin grams. And you know what, just for the sake of watching these units cancel out, I'm going to change kelvins to delta to degrees Celsius. It's okay. In this one specific context, it means the same thing. So don't worry about me doing that. It doesn't change the number at all. And then multiplied by the delta T. Well, what's delta T? Well, our final temperature, T final minus T initial, our final temperature is going to be 0 degrees Celsius. We're warming up the ice to 0 Celsius. We started at negative 15 degrees Celsius. So 0 minus negative 15 is going to be positive 15 degrees. That's good because we need only positive numbers, because if we're warming this up, our Q value should be positive, because that indicates that heat is being absorbed by the substance, well, by the ice. So we take 80 multiplied by 15 multiplied by 2.02, and I don't trust my math skills anymore to do in my head, so I'm just going to multiply this out. 80 times 15 times 2.02, that's going to give us 2,424 joules. Now, what I'm going to do here is I'm going to convert to kilojoules only because I know step 2 involves kilojoules. So convert to kilojoules just to make all the units match. 2,424 joules. And again, hopefully you know how to convert, metric units. 10 to the 3rd joules for every 1 kilojoule means the same thing no matter what unit you use, kilo versus base unit. And so that's just going to be 2.42 kilojoules. And that's it. All the other units have canceled out, so we're not going to have anything but joules or kilojoules. Degrees Celsius canceled, grams canceled. So the only unit that was left was the joules. And then the joules we converted to kilojoules. Again, only because we want all the units to match step 2. Of course, we could just convert step 2 to joules, but the number is going to be relatively large. Because it's going to be a large number of joules, it's better if we just convert to kilojoules to express big numbers. Use big units for big numbers. Otherwise, you end up with, large numbers, and who wants that? Okay, so that's step 1. This is our step 1. So just keep this in mind, write this down, put this number to the side somewhere because we're going to come back to it when it's time to add up all the numbers. Then we move on to step 2. Step 2 is to melt the ice. Melt the ice. No change in temperature. There is no delta T. Delta T equals 0. So we cannot use Q equals M times C times delta T. That formula is out. So instead, we just do a simple conversion. Here's the thing though, we're going to use the delta A, we're going to use the heat of fusion, right? But it's given per mole. So we have 80 grams of ice, which is water. So what we're going to do is we're going to convert, we know that 18 grams of ice, remember ice is just H2O, right? H2O, it doesn't, nothing has changed about ice. There's no reason its molar mass should be any different. Solid water and liquid water have the same molar mass. It's 2 hydrogens, same formula, 2 hydrogens, 1 oxygen, 18 grams. 1 plus 1 plus 16 equals 18 grams per mole, just in case there's any doubt. Okay, that gives us 1 mole of ice. And then we know that every 1 mole of ice requires 6.02 kilojoules to melt at 0 degrees Celsius. We take our 80 grams, and that's it. We just convert. It's a conversion problem. It's almost like stoichiometry, almost, because you're going from grams to moles, and then you're just going from moles to energy. So 80 times 6.02 divided by 18 gets us to 26.8. If I round, I get 26.8 kilojoules of energy. Notice we have a kilojoule as our natural unit because the kilojoules are built into this. So grams of ice canceled, moles of ice canceled, and we're left again with units of energy, which is exactly what we want. That's step 2. Again, just write that down somewhere, keep it handy, because we're going to add up all these numbers. I myself am just going to go back to these steps and rewrite the numbers down. Okay, that's step 2. Now we have one more step. Once we've brought this up to the 0 degrees Celsius, once we've melted the ice at 0, now we're going to warm the resulting water from this melt. This ice melts into water. Then we're going to take that 0 degrees Celsius water and warm it up to 75 degrees Celsius. So here we are. Again, we're back to water and using Q equals MC delta T. So we're going to warm up the water, the liquid water. So that's going to be, again, Q equals M times C times delta T. But this time, our C value is going to be that for water, not for ice, because now we're dealing with water, CW. CW is 4.184. Nothing's changed about that. That's the same old value you're used to. 4.184 joules per gram. And I'm just going to write this as degrees Celsius. Remember, it doesn't make any difference. Delta T. So what's our delta T? Well, our final temperature minus our initial temperature, obviously, but our final temperature is going to be 75 Celsius. Our initial temperature is 0 Celsius. We're starting at 0. So this is a positive 75 degrees Celsius. So we multiply all of these out. We get 80 multiplied by 4.184 multiplied by 75. We get a fairly large number, actually. Huh. That is, oh, I may have been wrong about the whole span of from 0 to boiling. Maybe I exaggerated a little bit about the heat of fusion, but heat of vaporization is definitely a large value. Okay, so still it's comparable. I get 25,100 joules. So let's convert that again. So we have grams canceling, degrees Celsius canceling, we end up with joules. Let's convert that 10 to the 3rd joules to 1 kilojoule. So that's going to be 25.1 kilojoules. Well, 75 degrees Celsius is a lot. And heat diffusion isn't that big of a number. The other one would be bigger. The other one would have been bigger. Heat of vaporization, if we were vaporizing, that would take a lot more energy. Heat of vaporization is always a lot bigger than heat of fusion. But in this problem, we don't use, notice what we didn't use. We didn't use anything related to steam, and we didn't use anything related to converting to gas or steam. We didn't need them because we only moved up to the middle of the liquid portion of the heating curve. We never went to the gas portion. We never tried to vaporize anything. Okay, so that's step 3. So we have 25.1 kilojoules. Step 2 was 26.8 kilojoules. Make sure your units are matching. You can't add different units together. And step 1 was 2.42 kilojoules. You know what? Let's just make it 2.4. Well, whatever. All right. Who needs that 2/100ths of a kilojoule anyway, right? Okay, so 2.42 plus 26.8 plus 25.1 gets us 54.3. I'm just going to ignore that last digit. 54.3 kilojoules. That is the total amount of energy to go from negative 15 degrees all the way up to 75 degrees for water, passing through one phase change and 2 warming phases, not phases like phase change, but just warming steps. That's our final answer. So it's the sum of steps 1, 2, and 3. 53,000 joules. And that was for 80 grams of ice, which isn't that much ice. So if you eat ice chips, this is how much energy your body, well, actually, let's see, 75 is a little bit high. You could calculate this at 37 degrees. That would be about half of this amount, about 12 kilojoules. Subtract about 13 kilojoules here, you have about 40 kilojoules. And you can calculate how much energy it takes your body to warm up negative 15 degrees Celsius, 80 grams of ice, to body temperature of 37 Celsius. It takes about 40 kilojoules. 40 kilojoules, what is that? In calories, 40 kilojoules, converting that to kilocalories, that would be 9.5 calories. Not much. So your body doesn't really expend a whole lot of energy to warm up ice to water. About 9.5 calories, or let's say 10 calories at the most. Okay. So that would be a complete problem. The only more steps I could add to something like this is if we went from ice all the way up to some, to 200 degrees of vapor or something, then we would involve these last 2 terms here. Since what we did had nothing to do, if you look at the energy curve, again, where did we move? We started, this was our starting point. We moved up, we moved across, we moved up, and we stopped right here. So this is, now, of course, it's conceivably you could have a question that maybe starts you right here and moves up to the vapor phase, and then you can calculate that energy. Or you can go directly, you can go all the way from solid, cold ice, all the way to superheated vapor. And you can calculate the energy associated with that, passing through both phase changes and all the different warmings along the way. Or you can go in reverse. You can go from, well, how much energy is lost when you're taking, say, for example, 37 degrees Celsius water, cooling it down all the way to maybe, say, negative 10 degrees Celsius ice. And you can calculate that. You can calculate anything along the curve given all the pieces of information that you need. And that's the idea. But remember, you do this in steps. You can't do it all at once. Whenever you reach a phase change, a plateau, you switch gears from simple Q equals MCAT to converting using the conversion factor, heat of fusion, heat of vaporization. So you cannot use Q equals MC delta T. You cannot, and this is the temptation, you cannot shortcut this. You can't say, oh, my delta T is simply negative 15 to 75. Let me just take the difference and multiply M times C times delta T. It does not work that way. You have a huge energy consideration when it comes to phase changes that is not going to be covered by Q equals M times C times delta T. If you do this, it's wrong. Not to mention, how on earth would you even try that when you have two different, if you're crossing phase thresholds, which specific heat would you even use? You can't use both in the same calculation. You know you're going to have to stop at one point, but don't go like, for example, don't go -15 to 0, Q equals that, and then 0 to 75 for the other one, Q equals that, and add, or something like that. You have to specify the energy associated with every step along the way, including the phase changes. And those are usually those are the biggest energy changes, especially if you deal with delta H vape. The heat of vaporization, I don't know if you've noticed this or not, but look at the heats of vaporization versus the heats of fusion. Just take a moment to compare and appreciate the difference between these. The heat of vaporization is more than 6.5 times greater than the heat of fusion. Again, that has to do with the fact, looking back at this picture, that has to do with the fact that you are blasting apart particles into gases. Vaporizing is a huge energy intensive process. You are not just loosening up the bonds like in a liquid. You are vaporizing, you're blasting this, you're atomizing this thing, you're completely disintegrating a material. That takes a lot more energy than simply going from solid to liquid, which just loosens the bonds, but doesn't really break the intermolecular bonds. That's why vaporization is so much larger. Consider this, 80 grams, let's take that as our number here. Just to vaporize that 80 grams at 100 degrees Celsius, let's go to our last term, just for comparison. This is not part of the problem now. Let me take my 80 grams of ice. Let's say, not even 80 grams of ice. Let's take 80 grams of water. 80 grams of water that's already at 100 degrees Celsius. It just hasn't vaporized yet, just hasn't boiled yet. What's the energy associated with vaporizing it, but keeping it 100 degrees Celsius, but converting it into steam? So 80 grams of H2O, we know that 18 grams is 1 mole. And we know that every 1 mole now is going to be 40.1 kilojoules. So let's see how this energy compares to taking this from ice all the way to warm water. And 75 degrees Celsius is not, that's really hot. That's not just warm. I don't know if it's scalding exactly, but it's pretty hot. So 80 divided by 18 times 40.1 gets us 178 kilojoules. No, I want to emphasize this, no temperature change. We did not even raise the temperature of this water by 1/10 of a degree. Not even 1 iota did we raise the temperature. And yet it cost us, what is this? More than 3 times as much energy, 3 times the energy of raising the temperature of ice, liquefying the ice, and then warming the resulting water up to 75 degrees Celsius, almost to the boiling temperature, still took 1/3 the amount of energy simply to vaporize that same quantity of water. That's how big the heat of fusion, the heat of vaporization energy process is. That's how much energy it takes to vaporize. So if you ever wonder why it takes so long to make water boil, that's the reason. It takes a lot of energy to turn liquid into a gas, to turn anything into a gas. So just appreciate that. That's a big energy investment to vaporize something compared to simply loosening up the bonds and liquefying from solid. And of course, the reverse process is also the true. If steam lands on you, it's going to give up a lot of heat to you. It's going to condense, but when it condenses, it's going to release all that thermal energy into your skin if your skin is in contact with steam. You have to be very careful around steam. Of course, like I said, there is the density issue. Water is more dense than steam, so there might not be as much coverage if you're covered in. Steam won't cover you completely, liquid water will. So there is that difference. But generally speaking, steam can cause worse burns per per gram than water at the same temperature. Okay, one more question, one more example. This is going to be a really short one. This is the kind of question where, I want to test, well, I don't want to, right now, I want to test your concept, your understanding of the concept, but I don't want you to do a bunch of number crunching, right? I don't want you to sit there and calculate all day. So what I could say is, well, here's a scenario. You don't have to actually number crunch. Just tell me which terms you need. In fact, to answer this, you don't even need the numbers. You don't even need these numbers. In fact, this doesn't even have to be for water. It could be for some unknown substance. Every substance has its own set of thermodynamic data, 3 different specific heats and 2 different heats of fusions. So, but I'm going to do this for water anyway. If I want to cool down steam at 100 degrees Celsius to water at 99 degrees Celsius, what pieces of information will I use? I kind of wish I recopied the heating curve here. Let's just go. So 100 degrees Celsius steam, 99 degrees Celsius water. Let's go back to the heating curve, whichever one represented water. Here's this one represented water. Let's just look at the heating curve and see which points we're moving through along this heating curve. So 100 degrees Celsius steam is this side of the flat region. We start here on this side. We're going to move here, and then 99 degrees Celsius. Okay, not to scale, but I'm going to put the 99 degrees Celsius right here. 99 degrees Celsius. Right there. So we moved through 2 parts. We crossed the heat of vaporization physical change. We converted from steam to liquid water, and then we moved along the water portion of the curve by 1 degree Celsius. T final minus T initial is going to be 99 degrees Celsius minus 100 degrees Celsius. That's going to be, or delta T then is equal to -1 degree Celsius. Not a big change, but still that gives us a negative sign because we went down in temperature. We're losing energy, even if it's only the energy associated with 1 degree Celsius change in temperature. So we move through 2 portions of this curve, the delta H vape and we turned it into water, and then we cooled the water down by only 1 degree. So that's 2 different energy terms. So let's come back here. So which pieces or what pieces of information will I use? Check only the ones that apply. And so I know it says check all that apply, but check only the ones that apply. Well, we had to convert from gas to liquid. So that's definitely going to involve the heat of vaporization. The only other thing we did was we cooled down the resulting water by 1 degree. It was still water. So we started with 100 degrees Celsius water, and we got to 99 degrees Celsius water. That's this one right here. And that is it. The rest of these are not useful for this particular question. Only this one and this one are needed pieces of information here. We phase change from gas to liquid, that's delta H vape, and then we cool water. Cool the water, and that's Q equals M times C times delta T, and that's C liquid water, not C gas. It's not for the steam. Remember, we're not cooling the steam. The steam was already at 100 degrees Celsius. All we did with the steam was convert it into water at the same temperature. So we are not using the specific heat of steam. If we were taking the steam from 150 degrees Celsius down to 100 degrees Celsius, that would involve the specific heat of steam. But since the steam itself is not changing temperature, we're simply converting the steam into water at the same unchanging temperature of 100 degrees Celsius. No specific heat of steam is needed. Only the delta H, the heat of vaporization, and then the converting of water. Well, the resulting water is simply cooled, so we use the specific heat of water. So just those 2 pieces of information. Is this an endothermic or exothermic process? we are cooling down. We're going from gas, we're moving from right to left, moving from gas to liquid. And then furthermore, we're going from liquid at 100 degrees Celsius, and we're cooling it to 99 degrees. Okay, that's way off. 99 degrees Celsius. So everything about this is removing energy from the water, from the H2O substance. Whether it's in the gas phase going to liquid, that's a loss of energy. And then going from liquid to cooler liquid is also a loss of energy. This is definitely an exothermic process. This substance is losing energy, going from gas to liquid, and then from liquid at 100 to liquid at 99. So it's all exothermic from the point of view of the H2O. Okay, well, I hope all of that was helpful and interesting and informative. Please let me know how it's going. Let me know how any comments or questions about this. This is it for the module regarding phase changes and intermolecular forces. And you can see the action of intermolecular, even though we didn't talk about intermolecular forces in this video, you can see their effects on the relative magnitudes of the heat of vaporization versus heat of fusion. And to a lesser extent, you can also see the effect on the warming and cooling of the different phases. But mostly you can see the phase changes are drastically affected by the strength of intermolecular forces. So they are always there working behind the scenes, making it difficult to phase change, I guess. Let me know how it's going. Let me know if you have any questions or concerns or comments. I hope to see you in the next video, which will be the next module. Take care.